Hi friends, it's been a little while. Neo Toy Story here with a video that kind of has several different topics in it, but if I had to narrow it down, I would say springs because springs are sort of a thing that's fairly interesting in 3D printing and worth a broader discussion. uh, these you've probably seen on sweatpants and hats and whatnot. They're a pretty universal thing that humans have created. I've always heard them referred to as toggles. I don't know if they actually have an official name. They probably do. They come in all different designs and they're pretty useful for a variety of things. Usually, a string goes through the notch or hole, and then a spring inside the cylinder usually clamps down. It's sort of a passive mechanical device. So a while back, I was like, I want to make one of those that uses a compliant mechanism and that for 3D printing. And this right here is pretty much the final draft of what I came up with. But I wanted to work through the chronology here just a little bit. Um, the principle was pretty straightforward. I was like, okay, I want like a spiral spring, or maybe it's called a leaf spring. I don't know. Like, there's a technical term for this, but the premise was pretty simple that basically a cylindrical spiral spring was going to be wound up and unwind. And the reason I wanted to do that was because I've made several springs now for various projects in for 3D printing, and the results are really bad, and that's mainly because of materials. As a lot of mechanical engineers will be aware, a lot of springs are made out of a specific steel called spring steel, which has special mechanical properties, mainly that it can flex over and over again without um, permanently deforming or fatiguing and breaking or becoming brittle. So it just keeps performing over and over again within the same approximate range mechanically. That's incredibly important, and that's something that's very hard to reproduce in 3D printing because we're using, PLA, PETG. There's a million different materials now, and some of them work really well for springs, and some of them are actually still pretty bad. Um, so I was thinking, how do I create a very robust spring? And this was basically my answer. And after I played around with this, I noticed that it wasn't really working out because the straight piece was bending, and I knew that was eventually going to fail, even though the premise was fundamentally sound. So I was like, what if pulling instead? So that was how I got to this design right here, and this was my first prototype that relied on pulling, or in this case, technically pushing. I'm going to slide this apart so you can see what's going on in here. So basically, the spring is fixed at the top of the mechanism by these little notches, and then this plunger right here basically pushes the spring down, so it's unfurling completely from a cylindrical shape, and that allows the force of the stress to be distributed across the entire surface area of the spiral instead of just on one edge where there might be a stress point. So that was kind of my premise, and I was like, okay, I want to refine that a little. So I refined the case and stuff, and I had to get the tolerances right in terms of the opening because I wanted this to be perfectly cylindrical when it was fully compressed, like an actual toggle. So that all the measurements were based on basically double the initial length of the cylinder for my flexing. But this measurement was off due to a few tweaks that I made. So I finally got around to doing the final final version. And this is not print in place, but it does print without supports, which is nice. It's also incredibly large, which, well, compared to, here's like a standard toggle, right? So it's like, I don't know, at least twice as large. And all the proportions, though, are 1.2 millimeter minimum wall thickness. So you could theoretically shrink this down to 50%, which, then would give you a comparable size, although this hole would be too tiny to really be useful. Anyway, so all of that aside, I wanted to put one of these together just as a demonstration. I probably should have done that first. But this is the latest iteration. So you flip the spring upside down and it goes into the inner piece, and you can just slide it into those little keys there, and that holds it in place. Not too hard to see this. And then the next piece to go on is the kind of the actuator, I guess you could say. So that cylinder goes into the middle of the spring there. And then finally, this whole thing goes into the sleeve. It's basically a locking sleeve, and there's little pyramidal indentations in there and a little pyramidal projection here that allows that to lock. So you just slide that in. There's a rail that guides it in. It's actually pretty easy to put together, and once that pops together, it's basically, I mean, you could force it apart, but it's pretty much fused at that point. So yeah, this is the compliant toggle design, and I've done quite a lot of repetitions of squeezing this, and it hasn't fatigued at all, and I think it shouldn't fatigue very much at all due to the way it's designed, and it's somewhat unique in the sense that it's taking a spiral spring and turning it into basically a fixed axis spring. So this, in a sense, is a spring module that basically has created this spring action here, which, there's a reasonable amount of force, strong enough to hold a piece of cord in there. And or you could recreate this module and put it into various devices. This length is actually fairly arbitrary. The distance between these two holes could be quite a bit wider, quite a bit narrower, depending on how much spring force you wanted and how much of a extension you wanted. And then, of course, varying the thickness of the spiral in there is how you would control for spring force. Of course, the thicker your spring membrane, the more fragile it's going to ultimately be to fracturing and stuff with materials. This is PETG. I'm gonna print some in PLA and see how they function, but this is more or less just a proof of concept for what is fundamentally a spring that is completely 3D printed, but actually will perform with similar repeatability and durability as a metal spring would in real life. One thing that really intrigues me about the future is the probability of using custom G-code, where you can actually have the extruder extrude a spring or a spring shape, whether it's really tightly wound or more loosely wound, directly on the build plate as a single pass piece of extrusion. I think there's some potential there because the laminar flow creates a fairly sturdy spring. However, the problem there, of course, is repeatability, because as most people will know who've played around extensively with PLA springs, no matter what configuration you use, whether it's like a bow spring or a coil spring or any kind of spring really, eventually after you flex it enough times, the PLA starts to just sort of like lose its resiliency, and that makes it sort of a poor material for springs. And PETG does work better, I've noticed. So this will probably be the best of both worlds. But anyway, oh yeah, one last thing I would just say, and this probably concerns anybody out there who's into 3D printing, FDM specifically. Get yourself one of the, I don't know if other manufacturers make them, but I got mine from Bamboo Labs. It is a super tack cold plate. So it's pretty cool. It's instead of a PEI textured plate, it's got a smoother finish, and it doesn't require to be heated to a really high temperature for bed adhesion to be effective. In fact, if anything, it's too good. I've had things stick to the bed that I could only remove with a combination of robust plate flexing and razor blade scraper leveraging just to get it off. But ultimately, the benefit is that you can print things that you couldn't have before, things that would have had trouble with bed adhesion. And let's see what else. Sounds like a commercial, but I'm not getting paid by anybody to do this. But anyway, it's just really great because my reliability of prints has gone way up since I started using the SuperTac cold plate. And I will say it's also nice to not have to wait for the bed to heat up. And there is a steep learning curve. I will say that. There is a learning curve. You will have to get used to it and figure out how to leverage its mechanical properties. But ultimately, it's infinitely superior, in my opinion, to the textured PEI plates, unless you're deliberately trying to make prints that you want to just quickly detach from the plates. So yeah, I wanted to, I made a video quite a while ago, and one of the things I said in it was like the one thing that 3D printing needed to improve was bed adhesion, and I felt that pretty consistently since I first started out, like, however long ago it was now. And then my first real 3D printer that I got to use at Ender had just notorious difficulty because it had a glass build plate, and that was hellish to get things to stick to. But things have come a long way, and these new SuperTac plates are just absolutely phenomenal. I get like, I'm probably like 30% less print failures with which is huge, massive difference, considering that before I was probably like maybe 1 in every 100 prints would fail due to bed adhesion issues, and that was after many years of ironing out difficulties. So yeah, still problematic though. As you can see, there's some distortion here that probably had to do with poor bed adhesion. So yeah, thanks for watching. I probably had some other things to say, but I've forgotten them, and see you around.